Hi everyone, my research is about modeling of absorption in pristine and defective metal organic framework materials. In this study, we focus on the interaction between UIO66 as a framework and its IPA, isopropanol alcohol, or nitrogen as a sorbate. Our ultimate goal is to understand the absorption, diffusion, and reaction of chemical warfare agents in moths. We start with small molecules such as IPA or nitrogen as a prototype that is easy to study experimentally. On the left is the moth we focus on is UIO66 because those advantages listed on the right, high degree of tolerability, chemical hydrothermal and thermal stability, and high specific surface areas. On the left is 1SBU second building unit of UIO66. It consists of a node that formed by 6 octahedrally coordinated zirconium atoms and 12 organic linkers. Each in the middle is the periodical structure. The dark blue sphere represents octahedral pole and light blue represents tetrahedral pole. Here is the IPA isothermal of pristine UIO66. We tested different potentials and compared with experiment. Those potentials doesn't make a lot of difference. You can see from the plot that all those simulation results significantly underpredict the loading at a relatively pressure above 0.005. The simulation is conducted at 291 Kelvin. Our guess for the description between experiment and simulation is missing linker defect. Here is the nitrogen absorption isothermals. The simulations are conducted at 77 Kelvin. You can see from the plot that all those simulations overpredict experiment. Our guess for the description is residual solvent in moth. Next, we looked at the effect of defect, because even in the pristine moth that the experimental group used, there are some levels of defect. Also, missing linkers are required to react with chemical warfare agent. No missing linkers means no chemical reaction. There are two common kinds of defect, missing node and missing linker. Missing linkers are by far most common. They are always present and they can be turned by changing the modulators. So we focus on missing linkers in our study. Here is our protocol of generating defective UIO66. First, we delete linkers from pristine UIO66. The defective level we studied is 33%, 17%, 8%, and 4%. And then we neutralize the open metal organic frameworks by adding hydroxyl group or formate groups. After that, we optimize the geometry using DFT calculation in CP2K and add didactic charges. Because UIO66 is a highly symmetrical structure, there are only two different ways of deleting two linkers in a primitive cell. The first one on the left is the simplified structure of UIO66. Those circles represent zirconium atoms. The solid line represents organic linkers. The dotted line represents the bond between zirconium and mu3OH. Those dots is those dots are mu3OH. In the middle is one with the structure. Those red line represent deleted linkers. The second one is on the second structure is shown on the right. Both of the deleted linkers are connected in yellow and blue zirconium. Simulation or calculation prove that the favorable way of deleting linkers is structure 1. So we calculate energy of different structures for certain 3% effective level structures. The structures we use for simulation is for the isothermal calculation is structure 1, structure 2 shown here. Those red circle represent where we added the capping groups. Energy difference between the two structures is 175 kilojoule per mole, and there are other arrangement of OH of capping groups giving energies between structure 1 and structure 2. Deleting one linker creates two positive charges in the structure. In order to neutralize the structure, we need to add capping groups. The capping group we tested first is the OH group. There are two choices for adding the OH groups into the structure. On the right, add different color to differentiate those four open metal sites. If you add the capping group to zirconium with the same color, we call it a transposition. And if you add the capping group to zirconium with different color, we call it a cis-position. It already proves that the Lorentz energy arrangement is trans-substitution. DFT calculation for IPA and for IPA pristine and defective UIO66 shows hydrogen bonding between IPA and mu-H or added OH. Here is IPA and here is one snapshot from DFT calculation. You can see that IPA is bonded to both mu3OH and added OH. However, if we use the standard UFF or Dryden energy parameters, it effectively prohibits hydrogen bonding with polar adsorbate. Why standard UFF or Dryden energy parameter prohibits standard hydrogen bonding? Since the LG radius, that's because the LG radius is too large. So, the IPA, the UFF sigma value, sigma radius of hydrogen is 2.571, and we use trap potential for IPA. The sigma radius for oxygen is 3.02, and so the average sigma value is 2.8 angstroms. So, but the typical hydrogen bond length is 2 angstrom between hydrogen and oxygen. There is no way for oxygen and hydrogen getting close to each other to form a hydrogen bond if you using a standard UFF potential. So we have modified standard UIO6 potential by using trap hydrogen by using trap LG parameters for all the oxygen and hydrogen atoms. Here is a comparison between the isothermals using standard UFF and the modified potential. On the left is Princeton, on the right is 17% effective structure. You can see that hydrogen bonding to mu3OH does not impact absorption of IPA in Princeton UIO66, but it has some level of impact on IPA absorption in defective UIO66, especially at low pressure. Here is isothermals of different defective structures. The temperature is 291 Kelvin. At low pressure, the increasement is caused by hydrogen bonding, and at high pressure is caused by geometry. On the right is the isothermal compression between those two 33% defective level structures. The red one is the lowest energy, the structure has lowest energy, and the blue one is the structure with highest energy. You can see there is a big difference at low temperature. So our guess is that the lower energy structure somehow prohibit IPA bonded to the added OH. Is OH the capping group for UIO66 synthesized in the lab? Experimental results show that defective sample has lower capacity at lower pressure, but higher capacity at high pressure. However, in our simulation, defective structure has high capacity at both low pressure and high pressure because the added OH groups. And you can see that they are, for low pressure, there are lots of IPA are bonded to the added OH or mu3OH. So we tested another capping group format from the literature. It could be the capping group could be either OH or format or other capping groups. For the experiment in this project, it's also proved that format capping group is more likely. Unlike hydrogen OH group, there's only one way of adding format capping group. Comparison between format capping structure and OH capping structure. You can see that I use the same color to represent same defective level. the triangle represents OH cat group, and the circle represents formate capital group. There is a big difference for 73% defective structures, but for other structures, there is no big difference. So summary, different ways of deleting linkers will affect the absorption. Potentials need to be modified to capture hydrogen bonding, and experiment in the excess capping group is format. And acknowledgement. Thank you.